All right. So I did agree, I graded a few students. I saw some problems. Some students I noticed, although you put correct answers, but I also noticed those students, they didn't understand how to get those answers. So I like to, in my explanation, I like to explain, the thinking, the background, so how you get there, okay? Because if you do not understand this part after I modify the question, then it's hard for you, okay? Yeah, because you get lost. You do not know where to go. I just modify a little bit, I add one condition. For example, I just change one condition. Then you get lost. Okay? Yeah. All right. So let me go through the details. Yeah. All right. Yeah. I just follow the order. Yeah. Some questions very easy. I use less time. Yeah. Also, I need to watch the time closely. Yeah. Right. The first question, the answer is 6, option B. But how to get there? There are 2 steps. Okay. The first step, first, you need to pay attention to the special structure in X squared. Yeah. All the terms with even power, that special structure is useful. Do not ignore it. Okay. All right. Then how to handle that? Yeah. Here I just give you the general idea. All right. So we can use another variable. For example, we use variable y equal to x squared. Okay. Yeah. Because in this way, we can simplify the structure a little bit. Because in this way, we can write, P of x in this a0 plus a1y, a2y squared plus a3y cubed plus a4y to the 4th and a5y to the 5th. Because after this variable substitution, we get a standard polynomial form. Okay, yeah, that's the standard form. Yeah. The original, this P, this X version, this is not a standard form. It's a special form. Okay, yeah. Because when we apply Horner's rule, we want to apply on the standard form, not a special form. Okay, special form, Horner's rule, you didn't use the power, the full power. Yeah, let me say the full power of Horner's rule. You probably only use the partial power. Okay, partial power. Yeah, not the full power. All right. So here, so we apply Horner's rule here. Okay. Yeah, you know that. All right. Then the importance, now I explain the importance of this variable substitution. Why we can save some multiplications. How to save? So here I'm talking about saving in computation. Some general idea to do saving in computation. There is a general idea or approach. So what's that? Reuse the resource. Yeah, put here. Reuse your resource. Okay, that's one way. When you have some resource, your resource is precious. Okay. When you have some resource, you try to reuse as much as you can. Reuse that resource. It's already yours. You already pay for it. Okay, so you should reuse it. Here, what's our resource? This is our resource. Okay, y equals x squared, because we already spent one multiplication here. That's what we pay. We already, pay something. Okay, yeah, pay time. So here, we spend some time on this multiplication. So we should reuse this as much as we can. Reuse this resource. Reuse this y value as much as we can. So that's why, all right, so the first time we use in the first term, but the second term we reuse it, okay? We do not do that computation another time. We just use it. Reuse the existing result and so on, okay? For all the remaining terms, we reuse our resource, okay? Yeah. When you reuse your resource, you reduce the redundant computation, okay? So what do you get? The result you get, you reduce the redundant computation. Otherwise, you would do a lot of redundant computation, okay? Second term, you do redundant computation. Third term, you do redundant computation, and so on, okay? You want to avoid that, okay? Yeah. And this general idea, later, we will also apply it to make our computation more efficient. Yeah, so here, through this question, so we learn that, okay? Yeah. All right. So the answer then, it's easy. By Horner's rule 5 multiplications. Yeah, because the degree now becomes 5, okay? Degree number 5 by Horner's rule. Then, to find y, we need a 1. So 5 plus 1 equals 6. So that's the final answer, okay? Yeah. Yeah. So now, after you fully understand this question, then if I modify, for example, one way I modify, I may change, x squared to x to the 4th, for example, okay? X to the 4th. So each term, the exponent, the power exponent, multiple of 4. That's one common modification I can do, okay? Yeah. So for other types, yeah. So yeah, it relies on my creativity. At this point, I have no idea. Yeah. Sometimes when I make the questions, I try to try to explore very deep my creativity. Okay, if I'm very creative, then I can make some tricky questions. So here I don't know. At this point, I don't know. Yeah. All right. Yeah. Some students enjoy. Enjoy.
If it didn't affect my life so much, I would be very interested.
Yeah. But under control. Yeah. So usually I won't give you too many such questions. Yeah. All right. Two or three. Next question, number 2. Yeah, this one. Yeah. First time. Yeah. So the first thing, you need to identify the structure. That's important. It looks like most of you, at the beginning, you did not know that Pascal's triangle. Okay, so here, if you cannot identify that, then it's hard. Okay, Pascal's triangle.
similar structures to Pascal's triangle?
Other, yeah, other similar. Yeah, interesting.
Is
Yeah,
there a
yeah,
rehedron or something?
right. Yeah, yeah, and yeah, yeah. I couldn't remember at this point. Yeah, it's also called related to Newton's formula. Okay, binomial formula, Newton's formula. You know, also written. This is a binomial. Okay, to n binomial form or Newton's formula. Okay. Yeah, formula. Yeah, but as I remember, this binomial expansion, binomial formula, it appears in your discrete math. Okay, in your discrete math, you have that formula. Okay, yeah, many formulas. Yeah. One of them, yeah, this one. Yeah. All right. Yeah, but that's a critical step. After you get that, there is another important thing. After you can identify, so you can quickly write it as 1 plus x to the 5th. Yeah. After that, then you need to do it in an efficient way. Yeah. So not just straightforward way. Okay. Yeah. So here, the best way, we know, we take square first. The second time we square again. Okay. Yeah. And after that, one more multiplication. This is the way to get power, 5th power with 3 multiplications. Okay. Yeah. 3 multiplications. Yeah. This is the technique we call repeated squaring technique. Okay. Repeated squaring technique. Okay. Yeah. Yeah. It is important. It is useful. Okay. Yeah. And this repeated squaring actually it follows our previous approach idea. Reuse your resource. Okay? Reuse your resource. Because after we take square the first time, the second time we should reuse it. Okay. When we do another square, yeah, we should reuse that. Yeah. Another square, we should reuse that. Okay. Yeah. Reuse it as much as we can. Question.
Way I did it 1 plus x plus 4
Equivalent.
It doesn't matter.
Yeah, it doesn't matter. Doesn't matter. Yeah. Here, just treat it as a compact form. Okay. You just write it. Yes. You know, yeah. You didn't use the second square, right? You just use another multiplication. Yeah. That's perfect. That's perfect. No problem. No problem. Okay. Yeah. Here, this way, I just emphasize squaring operation. I emphasize squaring operation. Yeah. Also a little compact. Okay. Yeah. No problem. Yeah. All right. So the answer 3 multiplications, not 4. Okay. Yeah. Question number 3. So now, I feel you should be fine. Yeah, because in the class, I talk about this question a lot. Okay. Yeah. So this one, you need to identify it is a exponential function of the form a to the nth with a greater than 1. Okay, that's important. That's all we need. Yeah. But that is a power function. Okay. Although that number is big, but the exponent is a constant. Even if it's big, it's a constant. Okay. Constant, it never changes. Okay. So this exponential function, finally, eventually, it will beat that big power function. Okay, yeah. But the question here usually, if you make your decision based on intuition, it's very likely you can get a wrong answer because your intuition, how to make the second one greater than the first one. Okay, yeah. Even, yeah, I remember some students, they apply the powerful calculator online, Wolfram Alpha before, you know. And that student drew two curves, you know, and the second exponential very flat. Yeah, that's not good. That's true.
Yeah, I was gonna say I did the same thing. I
Oh.
was just curious. to
Yeah,
see
curious.
How far it would go out.
Yeah.
And I kept trying to go out. I was using decimals instead of.
Okay.
And I kept going out. And I don't
Yeah.
know how many digits I got to,
Right.
but it was insane. And it still
Insane.
wasn't crossing.
Right. Yeah.
Fair enough, bro.
Yeah. You just imagine, how can you reach the end of the universe? You cannot reach the end of the universe, but it's there. Something is there, right? Yeah, eventually, yeah. But so I saw something did that way before. Then later I did the calculation. I can find expression for n that the second expression is greater than the first. So we can find a mathematical expression.
Yeah.
When n equals 10 to the 10th to another, 100th, yeah, that one, it will be greater than. Yeah, we can find that expression. Yeah, but on your computer, graph, you can never see what you want to see. Okay, yeah. So now you know the limitation of our resource. Okay, that's the limitation of our resource. That's not the limitation of the truth, right? Yeah, because your resource is not enough to help you see the truth. Okay, that's the point. That's the point. Okay, all right. Yeah, the next one, false. Yeah, if it is known that nobody in the world can improve a particular algorithm, then we can say that the system is optimal. It's not. Okay. Yeah. In order to say it's optimal, we have to rigorously prove it. It's optimal. If you do not do that, then someone in the future could improve it. There is a possibility some smart people in the future, they can find a better solution. Okay. Yeah. All right. Yeah. So that's the point. Number 5, the question. Yeah. So here, actually, this question, although it is simple, but it relates to a later question. But that one, remember, 5 elements, X3 in place relates to that. But I noticed many students miss that one. Okay, now this one, I believe most of you can get this one. Yeah. But that one. So here, we use this question, we prepare for that question. Okay, yeah. Here, yeah, because when you find the answer, yeah, so many students, they give me the correct formula. Okay, yeah. So they write, yeah, formula you can write from, from 10. Yeah. So that order also good. You know, this reverse order plus 9 plus 2 plus 1. Okay, yeah. So 1/2 times 10 times 11, okay, 55. So that is the answer. Okay, yeah, yeah. Why is that? Yeah, yeah, because here, when you count, yeah, yeah. So here, yeah, let me just repeat the procedure. Okay, when we do the counting here, we count the number of inversions. So when we count the number of inversions, and we assume, you know, for the maximum situation, what's the maximum situation? All pairs are inversions. If you can find a pair, that pair corresponds to one inversion. That's the maximum case. Okay. All right. So here, basically, we just count all the possible pairs. Okay. But when we count, all right, so first we start with the first element. Okay. First element, we can treat it as an anchor element. We make it as an anchor. Yeah. All right. So all the pairs start with the first element. Oh, I have some big important because I forgot to connect. Yeah, because it's in the energy saving mode. So I need to run out of power quickly. Yeah, it happened once before. All right. Yeah, treat it as anchor. So start with the same first element, then we count all the possible pairs. Okay, so that is n minus 1. Then with the second element as the anchor, then we count all the possible pairs, n minus 2. Okay, and so on. Okay, so the general formula will be n minus 1 plus n minus 2 plus all the way to the last one, 2, last one, 1. Okay, yeah. So 1/2 n plus 1. Okay, all right, yeah. And also, you need to know, this maximum number of inversion occurs on what kind of array? Descending order. All right, yeah. Yes, here, let me just use the, simple example here. Okay, descending order. Because later we need this information to answer our next question. Okay, so this knowledge we need it. Okay. All right, so let's move to question number 6. All right, suppose that a standard chess. Oh yeah, why not read it? This is a simple question, but so many students couldn't get a full credit, partial credit. So full credit, because here, even number of unit squares, this condition, okay? Yeah. We just need 6 square, right? Yeah. 120, right? Yeah. 120. Because sum of the last two, 100. Yeah, 36, 64, 100. Sum of the first two, 20. Right? Yeah, 120. Yeah. But I noticed some students add up all even and odd. So that's one common mistake, all even and odd. And another student add up all the squares, not even squares, just simple errors like that. Yeah, a simple question. Yeah. All right. Number 6. Oh yeah, number 7. Yeah. Number 7, the correct answer is C. Yeah. So let me explain why is that. Okay. It's simple, yeah, but we need to understand why is that. Yeah. All right. When we use the linear search on many different input arrays, here we already assume our algorithm is linear search. Okay. You cannot change this algorithm, right? Yeah. That means you write a program implementing this linear search. Okay, yeah, not the binary search, this linear search. Okay, yeah. All right. So then you process many different inputs. Yeah. Sometimes we have unordered arrays and sometimes we have ordered arrays. Yeah. So which are following about efficiency statements about correct? First one, we will get better efficiency whenever we process the ordered arrays. Here, imagine, although you enter ordered array, but computer cannot see it, right? The computer is blind. The computer is blind. The computer cannot see it. Okay? Computer just received an array, ordered or unordered, because your program, you make the computer implement linear search. So your computer won't apply binary search. Just still sequential linear search. Okay? Yeah. All right. So ordered, unordered. Can you see? How do you see the ordered one would give you faster search? Right? Because you don't know what is the search key. Right? You have no idea what is the search key. Given a search key, can you say in ordered array, we apply linear search, we will get a faster result than unordered? Can you say that? You cannot, right? Yeah. Yeah. So for that reason, because we assume the search key is a random one, right? It's a random key. Random key, if you ordered, unordered, when we consider the random property, the same. Probability is the same, right? At least we say the probability is the same. So then that's what we say, same efficiency, no matter we process ordered or unordered. Okay? No difference. Sometimes your ordered could be faster, but sometimes your ordered or it could be slower, right? By taking average, the same average efficiency. So you cannot see the difference. Okay, yeah. So here, one thing, yeah. From this question, we can learn, do not treat computer the same as human, as our programmers. We can see, we have eyes, so we know, the array is ordered. So then we will process it with better algorithm. But computer, if you write a code that's linear search, then no matter what, it just apply linear search. Okay, it never change. Okay, yeah, the computer. Yeah. All right, yeah, number 7. Number 8, true. Yeah, some students, I notice pick false, then you probably buy in your intuition, right? Yeah, you know, because here, actually, if you have a lot of real world experience, then you won't miss it. Real world experience, we know sometimes some large number probably not sufficient. Sometimes small number sufficient, right? Depends on different things you do. Yeah, so that's your real world experience. Yeah. Here, similar situation. Yeah. Many times when we answer questions, we rely on our real world experience. Okay. Yeah. All right. Number 9. True. Yeah. Well, it's very easy for some students. Yeah. So I haven't seen in this class, but here I'm talking about my previous classes. Yeah. Some students miss this question. They're based on the logic. And here, you know, sometimes logic, in order to apply logic correctly, you need to have sufficient knowledge. Otherwise, you apply your logic is wrong. Yeah, here. Let me explain. So those students here. If a given array does not contain any adjacent inversion, okay, yeah, then it does not contain any inversion. Inversion here, we talk about global inversion. Okay, the second inversion we mean global inversion. All right, yeah. Then by logic, yeah, some students, they just based on the logic here. Adjacent means local inversion, right? Here, there is no local inversion. Okay, so the question is, given array, there is no local inversion. How can you derive there is no global inversion? So here, this statement tells us no local inversion implies no global inversion, right? Yeah. So if we interpret in this way, yeah, okay. So the no local inversion condition, we have a no local inversion condition. Okay. Then the statement tells us it implies no global inversion. Global inversion. Okay, all right. Then some students use their logic. No local inversion. Yeah, because you only consider some local property. How can you get a global property by local property, right? In general, it's false, right? In general, here we talk about in general, okay? This in general, okay? In general, it's false, okay? So in general, so what do I mean in general, okay? All right, in general, that is no local property. Yeah, here I replace inversion by certain property, okay? No local property, certain property, okay? Some special property, okay? No local property in general does not imply, okay? Does not imply no local, global. Yeah. Does not imply no global property. Okay, yeah. So that phenomenon is correct in general, then we know in general there is exception. There could be exception. Here, this is exception. In our inversion case, we know no local inversion. That means the array is ordered. If the array is ordered, then no global inversion. Okay, yeah. Because for a special example, you cannot say it's false, right? Special example, you need to really get into the, intrinsic properties in this example. You cannot ignore the special properties. Yeah, all right, yeah. So here, let me say a few words on this in general, the general. No, in general, if some problem does not have local property, it does not imply no global property. Let me give you one example. Think about, we learned that greedy algorithm. Think about greedy algorithm. Do you still remember that? Greedy algorithm. All right, yeah. When we derive that Horner's rule, we use greedy algorithm. We do factorization as much as we can. That's the greedy algorithm. We do some special manipulation as much as we can. That's the greedy algorithm. All right, so now let me explain. The essence of greedy algorithm, the essence. Okay. So why many times we can apply greedy algorithm? Because it is simple, relatively simple. Okay, yeah, greedy, how do you interpret that greedy thing you do on some algorithm, the greedy thing? Do the best you can, right? Do the best you can. So what's that? The best you can, okay? So here I interpret as find the local maximum or minimum. That's the best you can. Local, okay? Not global, yeah. Because when you consider to get a maximum or minimum, you only look at the nearby data, okay? Yeah, a portion of, not the whole data. The whole data, it's too hard. If you look at the whole data, it's too hard. But here, let's just focus on a portion of the data. That's the local data. Then you find the maximum, minimum much easier, right? Yeah. So you apply the greedy strategy on local data. On local data. Okay, yeah, on local data. Then, now the result, the consequence of the greedy strategy. The greedy algorithm may not provide us the optimal solutions. Okay, the optimal solutions. What is an optimal solution? Optimal solution means you consider all your data globally it's the best solution. It's a global best solution, that's all. But you just give the, so you connect some local optimal, yeah, so actually, so it's something like you get to your destination, okay? So you start here, okay? You start here. Yeah. So your goal is here, okay? Your goal is here, all right? So you need to find a path. The path is your solution, okay? Path is a solution. So the path, if you look at a local path, always optimal, okay? Always best. Always best. So you're along path locally, always best, okay? But globally, it's not the best. Globally, because this way, there is another global best path than this one. So that's the point. That's the point. Yeah. All right. So from this example, usually when we have some local property, in general, we cannot get a similar global property, right? So local optimal property, so you have the local optimal property, no problem. Yeah, all the way to the, from beginning to the end. But you put them together, you may not get a global optimal property. Okay, it does not imply that. In general, it does not imply that. Okay, yeah. So that's the greedy algorithm. This tells us when you apply your greedy algorithm, you need to be very careful. Your solution may not be optimal. Okay, you have a chance to improve it. You have a chance to improve it. Yeah. Yeah. The reason, now you may ask, why people still use greedy algorithm a lot? Because it's simple. Local strategy, that's simple to apply, right? Global strategy, that's too hard. How can you, you know, when you consider all your data, it's hard, right? You only look at the local block, much easier. Okay, yeah. All right. So then, number 10, yeah, those 3 questions, if you use my hand, very easy. Yeah, highest order, order 2. Yeah. All the other, so the first, this is order 1, B order epsilon, right? Remember epsilon 0 less than epsilon less than D, and the D could be any small positive integer. Okay, yeah. So this one order 1 plus epsilon, right? Yeah. So then this one too. So 2 is the highest. Yeah. Right. Yeah. Okay. Yeah. Then the second one, lowest. Yeah. What's going to give me highest? Not, you need to. Yeah. So here I want to, remind you, read the question carefully. Okay. Read the conditions. You have plenty of time. So read the questions carefully. Okay. Yeah. All right. So here, the first one order is 1. The second order, yeah. So here we can write infinity. Yeah. Because it's greater than any positive, large positive number. Okay. Yeah. Although when you use infinity, you should be careful. Yeah. But here, temporarily, we use infinity here. Okay. All right. The C, we use 1 minus epsilon. Okay. D, we use 1 because we just keep the dominant term. Okay. Yeah. Now for your comparison, C is the lowest order of growth. Yeah. All right. Number 12, lowest order, log of n, epsilon order. Yeah. Still, this epsilon less than any positive integer. Yeah. Here, D equals this number. Yeah. Or yeah, I do not write D. Yeah. Here, I just write, order. Yeah. Yeah. Order. This is the order. Okay. This is the order. Here, the order is 1. Yeah. Cancellation. Look at the dominant term. Cancellation. Order is 1. This is 1/2 plus epsilon. Okay. 1/2 plus epsilon. So then the lowest is the epsilon is the lowest. All right. Yeah. So number 13, it's not hard. We use elimination method. Yeah. Yeah, but this thinking is useful. This thinking, yeah, actually later we need to apply this thinking many times. Yeah, so this thinking is important. Yeah, so let me, explain this elimination method. Elimination method. Okay, all right. Yeah. The median. So first we need to explain the median. Median is third position in the sorted array. Yeah. Third, specifically this third position we can interpret as third smallest or third largest. So you look at the same position from two directions, two ends, from left end smallest, okay, from right end largest. Okay, yeah, yeah. So this view is important. Yeah, so this view is so from left end counting smallest, third smallest, from right end counting third largest. Because if you look at from both directions, then you can get better result. Yeah. So when I move to our, yeah, we have a later question, number 23, that one, we will use the idea we're talking about here. Yeah. That one, also elimination method. Yeah. Yeah. All right, so here probably, yeah, probably one direction is already enough. Yeah. All right, so look at that. X1 less than X3 less X4, also X1 less than X2. Yeah. I hope you can notice that X1 less than many elements, right? Yeah, because X1 from the first condition less than 1 element, 2 element, and the third one S1 less than 3 element. So X1 already less than 3 elements in the array. All right, so 3 elements. 3, yeah. You already, suppose in a finally sorted array. So X1 must be before these 3 elements. Okay? And we know median is the third largest. If you count from right direction, third largest. So X1 cannot be third largest. Because already you know at least the 3 elements are larger than X1. So X1 cannot be the third largest. So this time you use this condition. Median is the third largest. So you can eliminate X1. Median is third largest. Eliminate X1. Okay. All right. Then number 14, yeah, I saw so many students gave me answer 6. The answer is 10, not 6. Answer is 10, not 6. Yeah. I haven't complete grading, so I will see how many of you got 10. Yeah. All right. So the logic, so here, so let's look at some general problem solving. Yeah. In my hint, actually, I give you that idea for the general problem solving. When you see similar questions, all right, so let me give you the special way to handle this kind of questions. All right, here, there is this condition. It looks like you feel hard to use this condition. So this condition actually messed up, okay? Without this condition, you're fine. But with this condition, suddenly you messed up, okay? Yeah, all right. So how about, let's ignore this condition first. Just as no such condition. When no such condition, remember we did that 11 elements maximum convert, that formula we used, right? In the 11 element question, the maximum number of inversions is this formula. Okay, here we apply that formula because no in place condition, so we don't worry about that. We just apply for n equals 5. You plug in 5, so you get 10. Answer 10. All right. Now, after that, then you add this condition back. Okay, add this condition back. But before you add the condition back, let's recall when we get a maximum number of inversions, what is the data look like? Descending order. Okay, yeah, descending order. All right. The data. Okay. Since it's a data descending order, X3 in place, it is compatible with that descending order, right? We do not need to do any change. We put X3 in place back into this descending order, no change. It fits there well. Our X3 condition fits in this descending order well, right? In place, we added it back. Nothing to do, right? You do not need to do anything. Yeah, that's what we need.
So if it was like in place on like the ends or something, we have to do something to change that final result. Like let's say
Right,
it was
right.
the extreme of one end.
Yeah. All right. Yeah, I understand. Yeah, let me guess your question. If I'm wrong, so you correct me. Okay. All right. I remember I gave another version of this question before. I said X3 is not in place. I gave one. Here, this semester I changed to in place. The previous semester I used not in place. Then you have to change, because descending order you won't get it. Yeah. So another version. So here I write another version. Condition X3 is just add not, okay, in place. All right, X3 is not in place. Okay. Under that situation, how do you fix it? This time you added it back. When you added it back, you have to do some work. Okay. do some work. That descending order, that means the answer 10 is incorrect. If you give me answer 10, it's incorrect because it's in place. You have to change that 10. Yeah, I answer your question later. Okay, all right, let me finish this. But how do you do it? Yeah, okay. Right. So it's hard. It looks like, move X. This time you need to move X3. Okay, yeah, all right. This time, think in another way. 10 cannot be the correct answer. What's the next best thing to get? What is the next best thing to get? 9. Okay, all right, 9. So now, can we move X3 a little bit? We try to get the 9 inversions. Okay, if you can make it, that's the answer. If you cannot make, yeah, so probably 9 is not the answer. Yeah, all right. Yeah. Yeah. All right. So do you like to try a little bit? Yeah. So here, all right. So let's do it in this way. Okay. Yeah. Let's do it in this way. Okay. Yeah. All right. All right. Let's still use 1, 2, 3, 4, 5. Okay. These 5 numbers. Right. First, this time, our logic is this. We know our goal, we try to find an input. X3 not in place, but our goal, we try to get 9 inversions. That's our goal. Okay. All right. How to do that? Yeah, let's do it this way. Let's take away X3. How about that? Let's take away X3 first. Yeah. Then 5, 4, 2, 1, descending order. Descending order. Okay. Yeah. Descending. And this descending order give us 6 inversions, right? All right. Now, we want to put X3 back to give us 3 more inversions. How about that? We put X3 back to give us 3 more inversions. Is that possible? 3 more inversions, but it cannot be in place, okay? It cannot be in place. That means this slot, you are not allowed to put X3 in that slot, okay? If you put X3 in that slot, it's in place. It's not allowed. It must be not in place, okay? How about, let's try, we put X3 in this slot. X3 in that slot, okay? Yeah, X3 equals 3, all right? Yeah. How many new inversions? How many new inversions? New inversions. 5, 3, is that inversion? 5, 3, is that inversion? All right. 3, 2, is that inversion? 3, 1, is it another inversion? So 3 more, right? 3 more. So adding together, we get 9. That's matching our goal, right? Our goal, 1 fewer than 10, all right? That's the best we can do because nobody can do 10, right? We know nobody can get 10. So the best that people can get, that's 9. Here we make it. We make 9. That's the best answer. How about that? So you can see for different conditions, the way you handle it differently. Differently. Okay? Yeah, differently. Yeah. Think about it. So from these examples, you can see to solve these computing problems. These are computing problems. Okay? These computing. So your logical reasoning and the techniques, your experience, logical reasoning, techniques, so many different ways to manipulate your data. Think about how many different ways we manipulate our data. You should be very creative to do these things. Very creative. Okay. All right. Yeah. Let me do one more question, then we take a break. Yeah. So question number 15, after you know the formula, it's pretty easy. Yeah. So M1 equals 2 to the N1 minus 1. Right? Yeah. M2 equals 2 to the N2 minus 1. Right? So now in the equation, you can simplify to get N1 plus 2 to the N2 equals that 1,280. Yeah, because you add that too. Okay. Yeah. But here, you just need to split the given number 1,280 into sum of power of 2. 2 power of 2 numbers. Okay, yeah. But actually, the way I feel better, you do prime factorization. Prime factorization. Okay, 2 to the 8th times 5. Now, after you do prime factorization, 5, but this 5 you can write as 1 plus 4. This 5 equals 1 plus 4. Okay, 1 plus 4. That's power of 2. 1 power of 0, 4. 2 to the 0, 4, 2 squared. Okay, so then you have 2 to the 8th times 1, that's 2 to the 8th, plus 2 to the 8th times 4, that's 2 to the 10th. Okay, yeah. So that's the way you split. This way. You split. Okay, yeah. All right. Yeah. So then I may modify. Yeah. So think about, I can give you a number. I may modify question in this way. We solve Tower of Hanoi 3 times. So M1, M2, M3. M1, M2, M3. So you need to split a number into power of 2 terms, 3 terms. Sum of 3 power of 2 terms, adding together, that equals the given number. But you do prime factorization, right? Yeah. Power of 2, extract the largest possible power of 2 out, then the remaining, it must be an odd number after the extraction. It must be an odd number. Odd number, you take 1 out, you get an even number again. That even number, extract power of 2 as much as you can to split. Think about in that way. Okay? Yeah. So in this way, even not 3 terms, if many terms, you can find solution, right? Think about it. Okay? Yeah. Any number of terms with this idea, you can figure out with this idea. Okay? Yeah. All right, so let's take a break.